Symmetries of flat surfaces of infinite type. This is joint work with Mauro Artigiani, Anja Randecker, Ferran Valdez, and Valdez and Weitze-Schmithüsen. The question of the day is, given a topological surface S, what symmetry groups are realized by various flat structures on S? So here I'm drawing some cartoon flat structures on the surface S and showing some symmetries that we see for the given flat structure. And notice if I give a completely different flat structure, the symmetries are different. Here we see an order 3 symmetry, for example. And there might be many other symmetry groups realizable by putting different flat structures on the surface, and the question is, what are the groups that are realized? In order to answer this question, we first need to know what a flat surface is. A flat surface is a surface with a metric that can be constructed as follows. We start with a countable set of finite Euclidean polygons. So I'm drawing an example here. And notice that these are not just rectangles. I've added a few additional vertices. And in each column, I draw a couple of rectangles that are half the height of the rectangle or rectangles in the previous column. And you can imagine how this would continue to form a countably infinite set of finite Euclidean polygons. All right, and then what we do is we would like every edge to be identified to exactly one other edge that is parallel and of equal length. And we identify by translation. So that's what I'm doing here. I'm taking these polygons and moving them around the plane by translation only, no rotation, nothing else. And I'm gluing together edges that are parallel and of equal length. And this would continue, as you can imagine. Now there are still some edges that are unidentified, and so I'm adding notation to show how to glue up the remaining edges. Again, the edges are glued together by translation. This forms a surface, and in this case it's a surface of infinite type, meaning that the fundamental group is not finitely generated. Here is another example where I've identified a number of squares using the method above. And now we're just going to explore the neighborhood of this point. And we'll walk around the boundary of the neighborhood counterclockwise. And what we see is that the boundary continues infinitely. The boundary is actually homeomorphic to the real line. It's not homeomorphic to a circle. And so the neighborhood of this vertex is not homeomorphic to a disk. This means that it's actually not a surface unless we remove the vertices of infinite degree, the vertices like this. So that's the last step in the recipe after identifying the edges. We have to remove vertices of infinite degree, and then that makes a flat surface. All right, now in this talk we're talking about surfaces of infinite type, and so we need to take a moment to understand ends of the surface and topology. So if we look at the surface S underlying a translation surface and create an exhaustion of S by compact sets, K1, K2, K3, so on and so forth, and then we look at connected components of the complements of the K. So that's the complement of K1, and we're going to call it U1. That's one connected component of the complement of K2, and we're going to call it U2, and notice it's contained in U1. Then we're going to find U3 over here, which is one connected component of the complement of K3, and it's contained in U2, so on and so forth. All right, and one of these sequences, U1, U2, U3, so on and so forth, corresponds to one end of the surface. So it can be thought of as one way to go off to infinity on the surface. And if you have two such sequences, V1, V2, V3, so on, that represents the same end as U1, U2, U3 if there is a V that contains the tail of the U sequence and there is a U that contains the tail of the V sequence. All right. And now there are two types of ends. As you look down your sequence of U's, for example, one possibility is that each U always has a handle, no matter how far down I go along my sequence. And in that case, we say that the end is accumulated by genus. Another possibility is as you go down your sequence, eventually the U's no longer have a handle. And then that is called a planar end, or an end not accumulated by genus. So we're going to make notation for both of these. E of S is going to be the ends of the surface S, and EG of S will be the ends accumulated by genus of S. These are not just sets. We endow them with a topology as follows. We take one of these open sets, let's say U2. It can be any open set in the surface. And then we consider the set of ends represented by sequences such that the tail of the sequence, some tail of the sequence, is contained in U2. All of these together form an open set in the space of ends. So these are topological spaces. And this allows us to give a classification of surfaces. This was given by Kerecchiarto and Richards. A topological surface S is determined up to homeomorphism by its genus and the pair of topological spaces, EG, ES. Now that we understand the topology of these surfaces, we can talk about their symmetries. Flat surfaces have two types of symmetries. The first type is the more obvious one. Shown here is an example of an isometry. All the points on the square torus move to the right by theta. Another type of symmetry is a Weitze symmetry, which I'll illustrate below. Starting with our flat surface, given by a countable set of finite Euclidean polygons with identifications, we apply a linear transformation, and that gives us a new set of polygons, and the pairs of edges that were identified, they were parallel and the same length before the transformation. That means they'll be parallel and of the same length after the transformation. So identifying them, you get another flat surface. And sometimes that flat surface is the same as the one you started with. The most familiar example of this is if you start with a square torus, apply a shear, and then cut, translate, paste, which doesn't change the flat surface, you see that you get the same flat surface as you started with. Here my copy pasting isn't as good as I would like, but if you marked that cut edge with a tilde, you would see that we have the same surface. So the group of linear transformations that give you the same flat surface that you started with is called the Weitze group. Now that you know what a flat surface is and also what symmetries of a flat surface are, we're ready to come back to our question. Given a topological surface S, what symmetry groups are realized by flat structures on S? Let's look at some previous work. So first I want to show you a theorem of Alcock in 2006. For any countable group G, there is a complete hyperbolic surface having isometry group isomorphic to G. So this is a theorem about hyperbolic structures on surfaces, but it inspired a number of similar results for flat surfaces. So here's what it inspired in the flat surface world. For the surface of infinite genus with one end, otherwise known as the Loch Ness Monster, because when you look at it like this, each handle looks like a different part of the monster's body, all countable subgroups of GL2R that do not contain contracting elements can be realized as Weitze groups. And contracting elements are matrices that when you multiply them with themselves again and again, it approaches the zero matrix. So this was shown by Prusitsky, Schmithüsen, and Valdez in 2011. Then Maluendas and Valdez in 2016 were able to expand to a larger family of surfaces, those where all ends are accumulated by genus, and the end space is a closed subset of the Cantor set of type K1. And they showed that for these surfaces, again, all countable subgroups of GL2R without contracting elements are realizable as Weitze groups. And when you consider a closed subset of the Cantor set, a special case is the singleton in which case we're talking about the Loch Ness Monster, and another special case is the entire Cantor set, in which case we are talking about the blooming Cantor tree, something that looks like this. You can think of their result as showing that all the surfaces, in some sense, between the Loch Ness Monster and the blooming Cantor tree have all countable subgroups of GL2R without contracting elements realized as Veitch groups. Finally, they investigated what uncountable groups are realizable. In 2011, it was shown that only a few uncountable groups are possible as Veitch groups for any tame flat surface. And what Maluenda and Valdez showed in 2016 is that as long as every end is accumulated by genus, all these possibilities are realized. These are such beautiful results that you might be thinking, what's left? Maybe we found all the Veitch groups that are realized. But actually, we haven't considered surfaces whose end space is not of type K1 and what countable groups are realized there. And actually, that is not an easy question. To approach this question, we were inspired again by a theorem about hyperbolic surfaces. So this is a beautiful theorem of Augab-Patel-Vlamis. If all ends are accumulated by genus and G is any group, then the topological surface S has one of the following properties listed in each bullet point below. It could be that the end space is self-similar, in which case G is realized as an isometry group by some hyperbolic structure on S if and only if G is countable. It could be that the end space is doubly pointed, in which case if a hyperbolic structure exists with G as its isometry group, G must be virtually cyclic. And finally, it could be that S contains a compact non-displaceable subsurface, in which case G is realized as an isometry group by some hyperbolic structure if and only if G is finite. This is an exciting theorem because it tells you a lot about realized symmetry groups for hyperbolic surfaces for all topological types where all ends are accumulated by genus. However, you probably have some immediate questions. First of all, what are these three topological conditions? Also, this is a talk about flat surfaces, so what about flat surfaces? Can we talk about their symmetries? And then if you look more carefully, you might notice that the middle bullet point doesn't have an if and only if, so you might be wondering about that. And then finally, what if not all ends are accumulated by genus? We'll approach the first question first. What are these topological conditions? Surfaces with self-similar end space generalize the idea of having one end. A topological space E is self-similar if and only if for every partition of E into finitely many pairwise disjoint Clopin sets, there exists an open set A inside one of the partitions so that A is homeomorphic to E. The surface of infinite genus with one end shown above, otherwise known as the Loch Ness Monster again, is a great example of a surface with self-similar end space, but so is the blooming Cantor tree, and so is the surface I've drawn on the right with countably infinite ends accumulated by genus going off to the right. A surface with doubly pointed end space generalizes the idea of having two ends. So the end space is doubly pointed if and only if there are exactly two ends whose orbit under the homeomorphism group of the surface is finite. I've drawn two examples of surfaces with doubly pointed end space here. You can see that the ends on top have a separate orbit from the end to the right and the end to the left. Those are somehow special and different. Another example is the plane with the Cantor set removed and then a point removed. So there's one end off the edge of the plane, and then there's one end from the point being removed, and those are special and have a separate orbit from the Cantor set. Finally, we have the situation where the surface has a compact, non-displaceable subsurface. This generalizes the idea of having three ends. A compact subsurface R is non-displaceable if and only if, for every homeomorphism F from the surface to itself, F of R intersects R. So as I said before, the surface below and to the left, which has three ends, is an example because the green subsurface is not displaceable, whereas the light green subsurface on the right is displaceable because there's a homeomorphism moving it to the darker green subsurface. So now we know what self-similar, doubly pointed, and non-displaceable subsurface means, and we know that every surface with all ends accumulated by genus has one of these properties. And based on that, we know a lot about which groups are realized as isometry groups for hyperbolic structures on those surfaces. So now on to question 2, what about flat surfaces? And that's where our results come in. We put out a preprint in 2024, hopefully it'll be published in 2025. We show that if all ends are accumulated by genus, then one of the following three topological properties hold. And unlike Augab-Patel-Vlamis's theorem, R3 are mutually exclusive. They form a trichotomy. The first one is the same. If the end space is self-similar, then G is realized as the isometry group of a flat structure if and only if G is countable. If the surface is translatable, which is a new word I haven't defined yet, but the end space is not self-similar, then G is realized as an isometry group for a flat structure if and only if G is virtually cyclic. And then otherwise, in all other situations, G is realized as the isometry group of a flat structure if and only if G is finite. Moving to another one of our questions, what if all ends are not accumulated by genus? In both these cases, it's possible to reduce the hypothesis slightly to include cases where not all ends are accumulated by genus. So this is a pretty cool theorem. It gives a nearly complete classification of groups realized as isometry groups of flat surfaces of infinite type. And we can go back and apply our proof methods to make Augab-Patel-Vlamis's classification just as nearly complete, meaning including cases where not all ends are accumulated by genus, and also making that middle bullet point about virtually cyclic groups if and only if. Alright, so remember that there's two types of symmetries of flat surfaces. We have a theorem about isometries. What about Veitch groups? So again, this result was released in a preprint in 2024, but we hope that it gets published in 2025. Let S be a topological surface with all ends accumulated by genus. Let G be a group. If the end space is self-similar, G being countable implies that it can be realized as a Veitch group for a flat structure on S. And if S has a compact non-displaceable subsurface, G being finite implies that it is realizable as the Veitch group of a flat structure on S. So this is also a pretty cool theorem, and it represents an advancement in the understanding of which countable groups are realized as Veitch groups of surfaces when the end space is not of type K1. But it is not a complete classification, and so there are questions remaining, which we'll come to in a moment. But first I want to revisit the 4 questions we asked earlier. So the first question was, what are all these topological conditions, which we more or less answered. The only topological condition I didn't explain is translatable. I won't define that for the sake of time, but what I'll say is that it's an adjustment of the doubly pointed criteria that allowed us to strengthen our results. It does still generalize the idea of a surface with 2 ends, and I'll draw a Venn diagram to show you how it fits in with the other properties that we did talk about. So self-similar n-space and doubly pointed n-space are mutually exclusive. Translatable, which is a term originally introduced by Anshel Schaefer-Cohen, sits here. And then non-displaceable subsurface that is compact sits over here. And we make our trichotomy by looking at self-similar n-space, translatable but without self-similar n-space, and otherwise. Those are the 3 bullet points in our theorem. Looking at question 2, what about flat surfaces? I showed you what we can prove about flat surfaces, so that question is answered. Looking at question 3, why is there no if and only if for the statement about virtually cyclic groups in Augab-Patel-Vlemis's theorem about hyperbolic surfaces? So indeed, we were able to promote that to an if and only if statement for isometry groups of flat surfaces, and our methods work going back to improve the theorem on hyperbolic surfaces. And finally, question 4, what if all the n's were not accumulated by genus? Can we say anything there? And indeed we did. In our theorem about isometries, and even in the theorem that's still on the board here about Weitze groups, in the bullet points where the group is not finite, we can loosen the hypothesis to include cases where not all n's are accumulated by genus. It is very tricky to find a flat structure to realize a finite symmetry group on a surface where not all n's are accumulated by genus. For now, that has eluded us. You might have one more question, which is why are there no if and only ifs for our Weitze group theorem? And this is because more groups are realizable. So we shouldn't look for an if and only if. It's not appropriate in this case. If you remember going back to the previous work, you can see that uncountable groups are realizable as well. And this reflects something that is very different about Weitze groups compared to isometry groups. Isometry groups act properly discontinuously on surfaces, and Weitze groups need not act properly discontinuously, and that's why uncountable Weitze groups are also possible. All right. So let's talk about what's next. What are the next questions? What's left to answer? So the most obvious is we only had 2 bullet points for our Weitze group statement. What about Weitze groups of translatable or doubly pointed surfaces? Surfaces that are generalizations of having 2 ends. So that remains open. Another thing is all the proofs here are constructive and they create infinite area. So this leads to the question, what about Weitze groups of surfaces of finite area? And I want to note that there are finite area surfaces of infinite type. There's plenty of those, lots of them exist. And then of course there are finite area surfaces of finite type. And actually that question seems to be harder to answer. There's a big open question for surfaces of finite type known as the lonely guy question, which asks, is there a Weitze group generated by a single hyperbolic matrix? So this is completely wide open for surfaces of finite type, whereas the previous work and results that I showed you today prove this conjecture for surfaces of infinite type. So there are a lot of great open questions left, and you should keep your eyes open for new results in symmetries of flat surfaces.